Hello everybody, my name is Thorsten Höffler. I'm a professor at ETH Zurich and I'm glad to welcome you to my talk, New Trends for Spin-based in Network Computing, from sparse reductions to RISC-V acceleration. So the SPIN project has actually been going on since quite a while, so it's in its fourth year now, probably fifth year, but the first publication was in 2017. And it has been driven by a large number of people, not just me alone, specifically Salvatore Di Girolamo, who is the technical lead, Daniele De Sensi, Konstantin Taranov, Luca Benini, and many other people helped establish this programming framework towards what it is today, essentially. In some sense, one of the most generic in-network compute engines. And today I'm going to talk about what happened in the last year, quickly repeating what we have been talking about much earlier, what the background of SPIN is, and what it used to be, and then moving into the hardware implementation, what it is today. So we actually have a full implementation and a 22 nanometer FDSOI process with the great help of Luca Benini's team. And then I'm going to talk about novel use cases in network compute, so like sparse reductions under the lead of Daniele De Sensi. So let me start right away with high-performance computing networking interfaces and how they developed in the last couple of years, which is really a very interesting history, and I've been following that history, fortunately, for the majority of my professional career. So it started in the 80s when I was born, in fact, so I wasn't really in the professional career then, with, as you all know, TCP/IP, Ethernet, sockets, this interface that we most prevalently have in the internet today, and even in high-speed data center computations, we're still using sockets. But in the high-performance computing environment, this was quickly replaced by more efficient interfaces, or seemingly more efficient interfaces, like the Scalable Coherent Interface, which proposed global coherent memory access. But that was not fast enough because global coherent memory access does not scale very far. It scales to relatively small systems, and then it gets relatively slow as you scale up. So what came then is message-based, and specifically active message-based interfaces that were implemented in Myrinet GM and MX, for example. They were pushing operating system bypass. Later, Quadrix, the first company or the first network that offered full protocol offload, a very exciting NIC, had some issues later, but was not too successful in the market. Later came the virtual interface architecture with the first zero-copy device, where we would directly deposit data into main memory, which is really the fundamental building block for today's remote direct memory access, which is an amalgamation of all of these previous active message-based protocols, OS bypass, protocol offload, and zero copy. So here we're talking about remote direct memory access, which showed up most prominently in the InfiniBand standard that now many people are actually using. It's very successful in the market. Just recently, NVIDIA acquired the company Mellanox, which has built its whole portfolio based on RDMA. And the Open Fabrics Alliance is an open institution or an open group standardizing the InfiniBand specification forward, that it's not just in a single company. Then Portals 4 is a very interesting extension to RDMA, which offers triggered operations. So this is one form of in-network compute. It's a very simple form. So you can basically define very simple programs in a very constrained language that are triggered, this is where the name comes from, based on incoming messages. And they can also trigger new messages. This was partially adopted in the libfabric interface. And then today, this is where we basically ended at 2020, today the smart NIC market is exploding. So there are DPUs, data processing units, IPUs, infrastructure processing units, like Intel names the DPUs, and network processing units as NPUs. So various companies have various names for these things, but at the end, I would all call them smart NICs. So there's some form of programmable NICs that aim at accelerating the workloads of these specific networks. But what is the fundamental abstraction down here? We had a whole set of fundamental abstractions. So what is coming next? And we'll see. But let me first summarize what the state of the art is today, what people are actually doing today somehow with these DPUs, IPUs, and NPUs, or how they are built. One class or one family of these smart NIC devices actually employs full-blown ARM cores. So full operating system. They're sitting outside the packet pipeline. They have a pretty slow access to the packet pipeline, but they're extremely powerful to process packets. Others are in the flow, in the packet pipelining that I would call flow processors with very limited flexibility. So here, Metronome and Barefoot have been pushing P4. Barefoot was acquired by Intel, so today that's part of the Intel networking group. And then fully programmable FPGA devices with limited productivity and limited silicon efficiency, but extremely flexible processing because you can implement anything you want on these FPGA devices, but they're quite hard to program in practice. But what is coming next? Well, what's coming next is really what I want to talk about. But I first want to motivate this SPIN model, of course. But I first want to motivate what is RDMA today and how can we improve it and what are the weaknesses of RDMA. So RDMA today, we have a network, as you can see on the left side. So in this case, it's a crane machine that looks a little bit like a zebra. We have an RDMA NIC. We have a PCI Express bus, we have memory down here, which is the input buffers, and we have a CPU complex up here, which processes the incoming messages. So when packets arrive through the RDMA NIC, they go through the RDMA processing engine, and then, of course, through the DMA unit into the input buffer. And then after they arrive in the input buffer, they have to be read by the CPU to be processed, of course, because otherwise why do we receive packets if they're not processed, and then generate new data and go into the computational flow. But if you now just look at the arrival rate of these packets, it's amazing. So with today's network interfaces, Mellanox Connect X6, actually today we can buy 400G networks, so let's just talk about the second one. So we get one packet every 1.2 nanoseconds. If you've paid attention in the previous slide, here are the latencies just going through the memory hierarchy. So 1.3 nanoseconds, just the highest level. So we get a ton of packets. Of course, there are pipelines, so the latency is not a big problem. We have to go with the throughput, but just comparing the two is several orders of magnitude difference. Just going through the through the PCI Express bus is a huge problem. And at the end, we have this device, this data processing device, the RDMA NIC that is built for moving data. It's built to process the RDMA protocol and write it through the DMA unit into user space of an application. This is the full operating system bypass, protocol offload style programming that we have for each of the arriving packets. But can we use this specialized architecture for other things? For example, can we do simple packet filtering, packet protocol implementations? That's not just RDMA on this NIC. And that's the question I want to answer today with a yes. I mean, now we have a specific architecture that can actually do it in practice. But let's recap a little bit. So we had all this history going forward into today's RDMA networking. But now we are talking about network acceleration. So let's look at the well-established compute acceleration. What happened in compute acceleration in the past? We had highly efficient, highly specialized acceleration devices like OpenGL or DirectX that were specialized for graphics processing, for highly parallel pixel by pixel rendering and processing and polygons and all of these things, very specialized. You could only have a specific use case to render graphics. But then one big revolution was started, mainly driven by the company NVIDIA, with this CUDA programming interface through generalization. So they invented a language that was able to express the specialized properties of these, or abstract the specialized properties of these highly parallel graphics devices into a higher level language where you can actually express things like matrix multiplications easier. And then later, OpenCL put this into an open standard, and OpenMP also adopted those. So somehow the compute acceleration was driven by generalization. We went from this highly specialized graphics processing units to GPUs, general purpose graphics processing units, nearly an oxymoron. Right? So general purpose graphics processing units. But that's really what it means. It is slightly generalized. It's still somehow a graphics processing unit, but we can generalize, or we can process it in a more general way, or program it in a more general way. What I want to propose with the SPIN interface, and we've been talking about this for years, so if you were listening to my talk last year, it was very much the same story, but now we're more precise. So we have today P4 and eBPF, very limited, highly specialized in-network compute interfaces. And the idea is to apply a similar generalization for data acceleration and not for data processing acceleration and not for compute. And here, what we are ending up with is a RISC-V-based SPIN implementation. And SPIN stands for streaming processing in the network. It's the interface we are pushing since a couple of years, as I mentioned, since nearly 5 years. And now we put this on the footing of an open source ISA implementation, RISC-V, to make it reality, to have a real processor. So Next comes, after all these interfaces, the streaming processing in the network interface with fully programmable packet handlers. So far for the motivation, well, how does it work in the abstract machine interface? So the abstract machine is really, we have a NIC, slightly different from a CPU because a NIC has a fast shared memory, which is really the packet input buffer. It has a packet scheduler where all these arriving packets are scheduled to various units. In this case, the units are the handler processing units. We have 4 of these units here in this view graph. We have the DMA unit at the bottom, which of course is needed to communicate with the host. Talking about the host, the communication is really going through read and write access between the NIC, the accelerated NIC, and the host memory, as we can see here. We have the CPU at the host, of course, because what the CPU does, just like the CPU, it orchestrates handlers on a GPU. The CPU here orchestrates handlers on the accelerated SPIN NIC and also manages the memory on the accelerated SPIN NIC. Very much the same model as CUDA, but not aimed at massive parallelism and massive compute efficiency, but aimed at massive data movement and data movement efficiency, which you could argue is actually gaining importance in the community and in computer science at large as we speak. So how does this work? Well, packets come in, are scheduled through these different units, through the input buffer. They are then processed on these handler processing units, and once they're processed, they're just moved by the handler processing units into the main memory in the CPU and then processed in the CPU. But all the data-heavy tasks are now performed on the device that is built for data-heavy task processing, and that is the handler processing unit or the accelerated smart NIC. So how do we program this device? Well, each message, as you probably all know, consists of multiple packets, and we process it packet by packet. We have 3 different types of processing kernels. So on a GPU, there's only one type of kernel, so it's a compute kernel. But on a CPU, on an accelerated SPIN NIC, we have 3 different kernels. So one kernel is executed for the header packet. This is what we call the header handler. It can set up a context for the message itself, which consists of multiple packets. All of these packets are now processed by the so-called payload handler. This is the handler that's the heavy work. The header handler typically sets up connection properties or message properties. The payload handler then processes packet by packet by packet, can be run on a massively parallel compute device. And then we have the completion handler, and the completion handler itself is just triggered after all of these packets have been processed. For example, it could clean up whatever the header handler has done, or it could somehow notify the user level process that the message has now been delivered in the processed form into main memory. So this is extremely simple to program. Basically what you do is you implement these 3 different types of handlers in C, just normal C, there's no magic to it. And then when you establish a connection, as you can see here, you just attach pointers to these 3 different handlers, and immediately it turns the connection into a processed connection. The processing is now happening transparently on the NIC, and the remainder of the talk will now go through how this actually works. Well, one more example. If we compare this to RDMA, on RDMA we initiate a message on the CPU, it goes to the network card then transports it over to the network card on the other end that deposits it into main memory, and only then the target CPU can trigger the response message, and of course then it goes back to the initiator. It's a simple ping-pong protocol here, but if we do the same thing with SPIN, the idea is very much the same. However, the card can immediately reply with a message. You see that's a significant latency saving, so we had about 250 nanoseconds here. Excuse me, 250 nanoseconds latency saved here, but it's even more significant if we have the multiple packets going. Excuse me. So for multiple packets, we would deposit the whole message into the target memory, and only then the target could trigger the response. And then, of course, these messages would be transported through the network in a pipeline fashion. But what SPIN can do, and this is pretty nice, it can immediately pipeline. So you can see the first packet already leaves the target NIC before the last one arrives. In fact, the first packet may arrive at the destination or at the initiator, back at the initiator, before the target has received the last packet. So we can streaming process through all of these messages at the same time, essentially. So it's a huge improvement. So now that concludes the first part of my talk, where I was just presenting a motivation. Now I want to present some use cases, just very briefly, because I have talked about those before. In case you've seen this talk before, you can probably skip ahead. And the hardware implementation then is absolutely a new piece that I want to discuss in great detail. And then the newest piece is now how do we apply SPIN in an in-network context where we can actually run this on switches and process this in an in-network reduction device that is truly in the switch, so involves no NIC. Of course, the SPIN NICs can coordinate with the SPIN switches in that context. Okay, so let me now talk about some in-network compute use cases. We have a whole lot of those use cases. We have a lot of students working heavily with our toolchain that I'm going to link to at the end. So you can also use our toolchain to try your own use cases with cycle-accurate simulations and also accurate network simulations. So we have accelerated data types. We have a file system implemented over SPIN. We have Zookeeper implemented over SPIN called ZooSpinner. We have erasure coding implemented, various quantization algorithms for collective acceleration or acceleration of Allreduce operations in machine learning, packet classification, and even serverless on the NIC nano functions we have implemented in SPIN. So I just want to discuss one quick example, the MPI Datatypes, because it is so impressive in some sense how you can process data movement very efficiently on the NIC. So what are MPI Datatypes? In MPI Datatypes, you can really translate arbitrary layouts from the source buffer into the destination buffer. So while the data may reside in the source buffer in a specific format, for example in a packed format, you could unpack it into the destination buffer at the destination, moving it through the network. The message passing interface, MPI, offers a specific interface to specify the data layout at the source as well as the destination. And there, as I said, there can be arbitrary translations in between. But typically, since the interface is quite complex, in the RDMA case, what happens is that all the data is sent in a packed format and it's deposited into the input buffer at the destination device in a packed format. And then in order to really implement the functionality needed, the destination device then unpacks the data into the destination memory in the right format. So we're now reading and writing the data twice. So we have to write it to main memory to just receive it, because that's what the RDMA NIC does. And we have to then read it from main memory to process it, to unpack it and write it back into the real destination buffer. So this gives you a certain bandwidth, as you can see here, so about 11 gigabytes per second for very large messages. For smaller messages, we get even less bandwidth and even higher communication time because, of course, the relative processing overhead is larger. So in the SPIN case, what we can do, we can instruct the NIC to immediately distribute the data without reading and writing it twice to and from memory, write it into the right destination buffer, because the NIC can now interpret the installed MPI data type at the destination and split the data the right way and just write it optimized to main memory. This gives us a 4x speed up in the asymptotic case, so we go up to 40 gigabyte, more than 40 gigabyte per second, with only 54 instructions in the packet handler. So this gives you a little bit of a feeling what this means, because we don't have to move the data back and forth from main memory to the CPU, and the instructions performed actually very, very simple. So we need only very simple CPUs, but extremely high bandwidths in this device. Okay, so that's really what we are going after. We could now look at real applications. This was just a micro benchmark that I showed you. Here are various high-performance computing applications. So here, WARF, as you can see there, the NAS parallel benchmarks, the spec benchmarks for various setups. The red line is our implementation on the SPIN device. The orange line is a specialized implementation where we really cut all the corners that we can cut and make it absolutely optimized for that particular case. And then the last line, Portals 4, is representative for any IOVEC or DMA scatter gather list device, what you can achieve. Because you can see here for the NAS benchmarks, for example, those are also pretty good, but not for all of them, as you can see in SW4 Lite. So here, I just discussed these. This is the SPIN line, this is the specialized line, and then the Portals 4 implementation. So I don't want to go too much into detail. You can look at those results. You will see that on average, the SPIN device is among the fastest. Of course, it's sometimes beaten by the specialized implementation, as you would expect for a specialized implementation. But of course, any specialized implementation loses flexibility. So we can see that even the specialized ones, they don't gain too much. Talking about the absolute speed up, we often achieve a speed up for relatively large messages of a factor of 5 to 10. So that's very significant for the data transfer itself. Then we have many, many more results that I don't have time to go into, but you have the paper here at the bottom. If you're interested in the kind of speed ups you can achieve, you can easily look this up in the paper and convince yourself that it's a good idea. Just another use case is a redundant array of inexpensive disk acceleration. So the idea here is that this is somewhat probably a redundant array of inexpensive nodes in some sense, so RAIN, because we are actually distributing the data in this example over various networks various devices in the network. So we have a server node and a parity node. This is inspired by the paper by Shankar et al. Down here. So what happens if a write request comes from the user? It's actually going through the server NIC. It's going to be processed as a write request by the server CPU, and then the server sends a parity update to the node on the other side, right? Then it's processed on the CPU there again, as you would expect, and the CPU sends an ACK back. And now you can already guess how the spin case will look like. We will just cut the CPU out. Oh, sorry, here is the RDMA bandwidth as usual. In the spin case, we just do everything on the NIC, right? The NIC just communicates with the memory directly, communicates with the target NIC on the parity node, where the CPU is completely out of the picture, and then sends the acknowledgement back to the original client. And we see that this leads to about 2x the bandwidth and 20% lower latency. You can guess why it's 2x the bandwidth, because we are saving the read-write cycle at the end. So it's always about 2 to 4x the bandwidth, depending on the detailed implementation, how many read and write cycles you have, and usually about 20 to 50% latency gain, which is quite substantial. There are many more examples. So we have fully one-sided secure data access with sRDMA implemented over SPIN. We have network offloaded data replication. That's just pure replication. There's nothing special about it. So there's not even applying parity codes. And then the erasure coding, as I just talked about, that is, you can also find this in the paper. One additional benefit is actually, since SPIN is like CUDA, you can just implement these parity codes within hours. You don't need to actually reduce, remove any firmware or update any firmware, like in this ENAC TRIAC example, where the authors updated the Mellanox firmware and had added some extensions, which was quite a bit of work, of course. So SPIN is user-level programmable. Every user can implement his or her own protocol on the NIC. So now, getting to the main part of this talk, which is the hardware implementation. So we have a full implementation that I will then briefly describe now, and then at the end I will talk about in-network reductions. Okay, so for the hardware implementation, I want to motivate you by a set of architectural principles for in-network computation. So first, we need low latency and full throughput. By full throughput, I mean full line rate. And in addition, we need support for a wide range of use cases. Of course, we want to have as many possible data acceleration applications as we can, so that there is a significant market for this acceleration device. Because if we only have 1 or 2 functions, the market may be too small to actually motivate the building such a device in practice. And it has to be super easy to integrate into existing NIC designs and existing switch designs. And I want to convince you in the next couple of minutes that we fulfill all of these properties with a relatively simple design. Okay, so the design principle here is general purpose acceleration, very much like GPU, so keep this in mind. So what are the architectural principles? As I mentioned, low latency, full throughput. These are the constraints that we work under. Low latency, I mean double-digit nanosecond latency, which is very much in line with today's high-performance switching devices. For matching, of course, the processing time may vary depending on what your handler time is, or how heavy the processing is you want to perform. And we must always be able to run at line rate. Of course, in order to run at line rate, we need highly parallel implementations, highly parallel devices, because 400G is a lot. It's 50 gigabyte per second, and we now need to process this on relatively lightweight RISC-V cores in our example, so we need lots of those cores. And now you could actually look at the theoretical requirement, how many handler processing units of the type I'm going to talk about in a couple of minutes do we need in order to support handlers running for a certain time. So here we go between 1 and 4 microseconds. Our device is clocked at a gigahertz, so 1 microsecond means 1,000 instructions we can execute. 1,000 instructions is a whole lot. Right? Remember the handler I showed you, the example handler with the data type processing, takes about 56 instructions in the specialized case. So that is quite little. The non-specialized case will actually take more like 1,000 to 2,000 instructions, but for 200G you can see that's about 50 cores. For 400G, 2000 instructions, that's about 100 cores. Of course, it's linear. So just keep that in mind in order to process packets for a certain amount of time on a fixed processing device. You need more and more cores, of course, more and more throughput, and that's pretty obvious. The scheduler itself also has to be fast because packets arrive every 1.2 nanoseconds, so somehow we must schedule these messages very fast and also in a pipelined way that we can sustain the throughput. We also want the processing itself to be fast. So fast memory access. We have single cycle memory access to the closest memory, and we have a couple less than 10 cycle access to the next larger level 2 memory in our devices. So, okay. Furthermore, we want to really support a wide range of use cases, as I already discussed. In these use cases I mentioned before are all supported in our architecture, so there's actually nothing that we are afraid of in some sense, so you can throw arbitrary workloads at us. However, we want to emphasize it's an accelerator for data movement. So you cannot solve matrix multiplications on the device, or you can, but it's going to be extremely inefficient. It's not a compute accelerator, it's really a data movement machine. So everything that has very little processing but is very data intensive is very useful, or relatively complex protocol processing, like the zoo spinner example, where it's all about consistency, or the SPIN-FS, where we really have to work with many, many different clients at the same time. For this, we have specifically support for stateful computations, so that for a connection you can have a state, or for a packet, for a message you can have a state, and each packet is then routed to a processing unit that is actually that can access that shared state for either that connection or that packet itself, that message itself. Furthermore, we have strict isolation between handlers, so that we can enable multi-tenancy. We can have multiple users on the same network card that are strictly isolated, so that cannot read or write each other's memory through memory protection mechanisms. Okay, so now the last part I want to convince you of is this easy to integrate. It's probably the easiest part to convince you of, because just look at this view graph. What we have here is the architecture of a network, a normal network card. So we have an outbound engine, inbound engine, a command unit, a network interface, and a host interface. This is how pretty much every NIC works today. All we do is we add this yellow box in the middle. It's the SPIN unit. The SPIN unit is directly connected to the inbound engine. The inbound engine may skip the processing unit. Of course, there may be streams and packets that don't have to be processed, that are just going directly to the host. Whenever a packet is to be processed, it goes to the SPIN unit. SPIN unit can itself send data through the outbound engine, so it has to have an additional connection to this. It can also issue commands to do so, and of course it can communicate back and forth with the host. So you can see the SPIN unit is kind of the heart of this programmable architecture. It's connected to pretty much everything else, but it is part of the inbound engine for packet processing, or inbound engine data path for packet processing. So we will convince you that this unit is very area efficient, so it's less than 20 square millimeters, and it's extremely configurable, hardware configurable in some sense. And of course, general purpose programmable, that's the major piece. So in order to achieve all of this, we chose to collaborate with Luca Benini's group, which has the PULP parallel ultra-low power platform. These are all the keywords we want: high parallelism, ultra-low power. Of course, it's also very small, and it's also pretty impressive in terms of data movement capabilities. What it's not super compute intensive, but there are compute intensive configurations that we are working on in different projects. So the unit we are using is just the base unit with the base instruction set. There are accelerator versions of the PULP project, which of course in the SPIN, compute accelerator versions, which in the data accelerator context of SPIN don't play the largest role. So let me look a little bit more in detail here at the structure of this PSPIN unit. So what we have is, of course, memories. Most of the chip space, most of the space we invest is into memory. We have L2 packet buffers, program memory, and handler memory. So I'll talk about that in a bit. We have a hardware packet scheduler in the device, because in software that was too slow, and we have 4 clusters in our prototype device. Each of those 4 clusters has 8 cores. These are these small H's here. It has a DMA engine, and it has a cluster scheduler, the C-SCAD, and it has a directly accessible, single cycle accessible TCDM memory. Okay, then we have a DMA engine for off-cluster accesses, so we can actually communicate with the main CPU. We have a command unit which where we can issue commands to. And then there's, of course, the usual monitoring and control units as you have in any such block. So from an application perspective, how does it now work? So from an application perspective, as I mentioned in the abstract machine model, the CPU, the programmer itself, specifies various handlers. So here we see two example sets of handlers, telemetry, excuse me, for a telemetry and a filtering application. So we have header handlers, packet handlers, and a completion handler for each of these two. We install those in the level 2 fixed size program memory. Of course, these handlers also have to fulfill some constraints in terms of their size. Second, we have to define an execution context so that the inbound engine itself can match packets to a particular application, so to a particular user as well. And then we also deposit state and buffers into the user level application here. So we have the state over here, which is going to be deposited in the handler memory, and the buffer itself, which is then going to remain at the host memory. So here is the state, as I mentioned, and the buffer moves into the host memory. This is where the data is then deposited into user space directly. And of course, the programmable SPIN unit has access to both the on-chip state, which is the fast access. You could argue this is some kind of cache, local managed, explicitly managed cache. And the buffer at the host is now the destination buffer where I'm moving the data after processing has finished. Then we have to, of course, define matching rules. So somehow we have to now identify how our stream is going to be identified. Well, we have to specify how our stream is going to be identified such that it's routed to the right user level program on the SPIN NIC. Okay, from a networking perspective, it looks relatively similar. So we have all of these handlers installed. So we have a filter handler, we have state, and we have host buffers. Then, of course, we have a packet that is coming in. And we assume now the handler has been pre-set up, or the set of handlers. And we have the inbound engine writing the packet to the level 2 packet buffer. And now it informs the PSPIN unit that a new packet has arrived. So what does this PSPIN unit do? Well, it schedules the packet to a cluster. The cluster internally uses the cluster scheduler to then schedule the packet onto a particular core. And of course, it makes sure that the cluster itself has access to the context, the correct state. So the schedule itself is a little bit more complicated. It routes packets to specific clusters that have access to the application state, because otherwise that would be quite bad. So the whole scheduling overhead itself, for very small packets, it's about 12 nanoseconds. For slightly larger packets, because it needs to copy these packets, of course, it's about 26 nanoseconds. So it's within tens of nanoseconds. I can invoke a function on a core on the PSPIN unit, right? So that's the time it takes to just get to the core. But what is most important is actually the data path. And here I'm explaining the data path, or I'm showing the data path for a 400 gigabit device. That was our target for the implementation that we have. And we have, of course, these various memories that we have: packet memory, handler memory, program memory. We have these various clusters here with our memories. We have a host interface. We have an I/O MMU. We have a host access. We have an off-cluster DMA engine, which goes to the host interface. Then we have a NIC inbound and outbound engine, and then a host adapter. So there are lots of interconnects here that I don't want to talk about in great detail. They have different widths. One is 512-bit, the thicker ones, and the smaller ones is 32 bits, just leading to the cluster. So these are all XE interfaces in this specific implementation. I just want to highlight one particular, or two particular scenarios. So one is the data stream is received from the NIC. So there's a 400G stream coming. The 400G stream goes from the NIC inbound engine through the first interconnect into the packet memory, and then on demand is copied, well, whether it's needed or not is specified in the handler itself, is copied to the L1 memory. It may actually reside in L2 if the handler is not processing the message, but just the headers. Then I can forward directly from this memory. But let's talk about the processing, fully processed path. It's going into these different clusters. And then once processing has finished, the data resides in L1, but is then moved either to the NIC outbound engine, so leaving the cluster again, or leaving the machine again into the network, or through the off-cluster DMA engine, moved into the host main memory. So as I mentioned, a SPIN NIC can either, or the SPIN processing unit can either trigger the generation of a new message to send it to a remote device, or it can actually just deposit it here into the host memory. Okay, so Then if we have another data path where we could come from the level 2 memory if we have not processed the packets, actually, as I mentioned before. So these packets would be directly forwarded through the NHA interconnect either to the outbound engine. I can send those to another machine as well. Like imagine just implementing a broadcast protocol. I don't need to copy the messages through the L1 of the cluster. The cluster would just say, well, I have these messages still sitting in level 2, just forward them to the NIC outbound engine, or we could also forward them directly into the host CPU. For the broadcast example, I would actually do both. I would receive a message on the inbound engine into L2. I would trigger new outbound engine messages, as we see here, and I would trigger a copy to the main memory at the host CPU, because of course the host CPU wants to receive this message as well. So this is the full data path, and we can saturate full 400G in and out, full duplex with this architecture on this particular machine in simulation. So how does this look like in practice? Well, we actually designed this in GlobalFoundries 22 nanometer FDSOI process, clocking at 1 gigahertz. This is exactly the architecture I just described earlier. This is about 95 million gate equivalents, which is equivalent in that process to about 18 square millimeters with a 70% layout density assumption. Uses about 6.1 watt at 98% toggling rate, which is somewhat of a worst case. So it would be much less in the average case, of course. But even this 6.1 watt is very, very small. We can have a breakdown here, but let me actually discuss the breakdown with this diagram. It's much nicer to see. So we have these 4 clusters here. So you can see here, cluster 1, cluster 2, cluster 3, cluster 4. Most of the chip, in fact, is a level 2 scratchpad memory. So 60% is scratchpad memory. The remaining 40%, or nearly 60, remaining 40% are these 4 clusters. Most of the cluster, again, is level 1 scratchpad memory. You can see about 80%. And then the core itself is actually pretty small, in the logic of the core. So you can see this is a data movement into data intensive engine. More than 80% of the chip space is just some form of memory, explicitly programmable out of these memories so that we can orchestrate the data path to be most efficient. If we compare this to a Mellanox Bluefield device, which has 16 A72 cores, we would estimate the die area at about 51 square millimeter, and the energy consumption actually higher than our device. So as I mentioned, now we need to do a little bit more. So now we have the PSPIN unit, but how do we now integrate this unit into the network card? Well, we also have to modify the inbound engine, because what the inbound engine now has to do, in addition to just forwarding messages into the main memory, it has to identify, so it has to parse the header of each packet and has to identify whether these packets are in fact routed to the host interface, so going directly into main memory, or to the processing unit, the PSPIN unit, so either going this way or this way. And we do this with very simple match action tables. You can compare those to P4. So we basically identify flows with simple match action rules. Then on the host interface, how does the programmer now interact with this? I already mentioned this in the programming section. The idea is that the programmer, with each new connection, just specifies these 3 different types of handlers. The programmer could even either have a standard queue pair, as I mentioned before, as we all know, or a processing queue pair, which is then programmed by processed by the PSPIN unit. A processing queue pair is simply a queue pair that has all of these 3 different handler types attached. It doesn't have to have all of those. Some of those could be null pointers. 1 is okay, so at least 1 handler type. And then the processing will just happen in the PSPIN unit. Okay, so now I hopefully convinced you that we met all of these requirements. So let me summarize this again. So the low latency full throughput requirement is met with the 32 core design that is sufficient for processing for all of our use cases, for sufficiently large messages, processing 400G streams. The fast scheduling is tens of nanoseconds. We could actually scale this up. And the explicit memory access, we have an extremely efficient memory access memory subsystem with a single cycle level 1 memory and less than 10 cycles a level 2 memory, which is of a substantial size. Then we have support for very large range of use cases because we support stateful computation and full handler isolation, which means we can expose this interface to any tenant in my data center. So we don't have to trust each other. This is also quite powerful. Most of today's accelerated networking interfaces do not have this level of isolation, do not allow multi-tenancy, do not allow user-level access in an untrusted environment. The PSPIN implementation does. So we have this very powerful SPIN programming model, which is as convenient as CUDA, I would say. And then, of course, this is all implemented on a RISC-V CPU in the PULP design. And the handler isolation is a very simple memory protection mechanism. Then easy to integrate. Well, if you have your NIC, it's relatively simple to implement all of this on your NIC because the device is area and power efficient and it's highly configurable. So you can actually take this efficient design and just change the number of clusters and the cores per cluster, and all of this is part of the PULP framework, and build the machine for your bandwidth and your requirement, and just tape it out essentially. So that's how ready it is, and you can pretty much download it from GitHub. So that'll come towards the end. But before that, I want to show you some more experimental results that we gathered with more complex applications and cycle-accurate simulations. By the way, all of this has been published at ISCA 2021. If you want to look at any of the details, you can find the full paper there. So we look at 3 different types of handlers with various examples each. We look at packet steering handlers, where we really just decide where does the packet go. For example, in the filtering case, we either discard the packet or just move it forward. In the data type case, I already explained to you, we just move the packet into different memory locations. We have a data movement case where we have to look up specific locations to deposit the data to, like in a key value store. And we have full packet processing, where we need to look through all of the content of these packets in order to figure out what to do with them. Of course, full packet processing is the most demanding use case in our particular case. So here you see various examples for different packet sizes. So the left bar is always 64-byte packets. The next bar is 512, and the rightmost one is 1 kilobyte packets. Then you have the various use cases down here, and you have the lines for 200 gigabit and 400 gigabit per second. And you can see that for sufficiently large messages, pretty much all of the examples achieve 400G network throughput. I don't have more time to devote to this, but again, you can just look at the paper, and you can also contact us later. So here, one interesting insight, and this is what I showed before, but it's now the kind of the inverse of that plot, where as the packet size of a message goes up, so the larger the packets, the more time, of course, I can devote in the handler, right, to process this on our particular 32-core architecture. So this is of course logical, but it's still pretty good to understand this for so 1 kilobyte messages can actually take on 400, if I want to run at 400G line rate, a single handler execution to process a single 1 kilobyte packet can take up to 550 or something nanoseconds. So this is actually quite substantial. So there is a lot of compute bandwidth here, and if you just want 200 nanoseconds, we can have more than 200 gigabit per second. We can have more than 1,000, probably 1,200 nanoseconds processing time on the device. So that is actually not too bad. But of course, as I said, you can configure the device as you want. You have to hit the ideal working case for your particular scenario. But since we want to support general purpose packet processing with our ideas, we keep it configurable. So now, how does this compare to other NIC architectures, other potential architectures? For example, if I would put a Xeon or an x86 CPU on my NIC, if I would put an ARM CPU on my NIC, or if I would put our little risky RISC-V core on my NIC. And so we collected some data just for the same use cases, but now we are not looking at the full processing throughput, we are just looking at the CPU, at the per core throughput. So how fast can we process, let's say, aggregation on either an Intel CPU here in red, or a Zynq, AMD Zynq, ARM Zynq CPU, or in the PSPIN CPU per core. And you can see that, of course, the Intel core is almost always fastest, well, because it's a very powerful core. But the PSPIN core, which is a very slow core for these data-intensive tasks, is quite often not too far behind. And if you look at the actual size of those cores, like for various technologies, but we can compute the area per processing element as scaled by the technology node, and you see here Intel's size per core is nearly a factor of 60 versus than our than the PSPIN implementation, and the Zinc ARM core is more than a factor of 3 VARs. So now we can normalize this and we can look at the per core throughput per area. So that's now gigabit per second per square millimeter core space. And now we see that SPIN is winning in pretty much all cases, because this data movement accelerated architecture is very efficient in terms of size, chip size, but also in terms of energy. So energy, we don't have explicit numbers because it's hard to determine for these other architectures. So as I mentioned, there are many, many more application examples. You see this plot on the left here. There are many more plots that I could have talked about. I just chose a subsample where I believed that you would be most interested in. And you can, of course, look at the paper that appeared at this year's ISCA, and here is the link down here. So I want to change gears and get to the last part of my talk, which is really in-network reductions. So let's now take this idea of processing on the target NIC, but actually let's take this a bit further, push it fully into the network. Let's process in a network switch, but let's use the very same architecture. Let's use the PSPIN architecture I just talked about, move them into switches, or move these cores into switches, and then see what happens. And we have one particular example that we worked on. This is in-network reductions. So in-network reductions is a very important use case for many machine learning workloads. So the idea here is that all of these, or some subset of these endpoints, so these blue ones here are network endpoints, these green ones are switches arranged in a fat tree. Each of those, some subset of those blue nodes here, host 0, host 1, and host 3, have some data. And what they want is they want to compute the global sum of the data. And typically in machine learning use cases, this data can be quite large. This data can be gigabytes of size and occupies a lot of bandwidth to reduce or to sum up all this data, but very little compute, because it's just summing it up. The arithmetic intensity is pretty bad in this sense. So it's not a matrix multiplication. So what do these endpoints do? Well, they have to send their data into the network to the next green switch. So each of those does it. Then in the in-network reduce case, the green switch will actually already compute the sum. And you see that it has already halved the data volume. So if I was going to send this data, let's say to this host on the other side, it's already, by summing it up the tree, it has halved the volume. And then once it has all been summed up at the top of the tree, it's just sending the result back. So the upshot of this is that I can save about 50% of the network bandwidth to perform this in-network reduction, as opposed to an endpoint-based reduction. So the in-network is crucial to gain a 50% or a 2x network bandwidth gain. Okay, so there are of course many products that do things like this. So here you can see a lot of different papers, and again I ask you, if you want to know all the details, to refer to the paper at the bottom that is going to appear at Supercomputing 2021. It's already on archive, that you could also download there directly. Just to mention, Mellanox's Sharp is probably the most used one in practice today, because it's a product, you can just buy it. A SwitchML is an idea to build this on top of P4 programmable switches. This is also a very interesting idea that you could also apply in practice. Many of the other ones are also partially applicable in practice, but not as widely spread as these two. Okay, so then I have 3 different functions here. So I have 3 different functionalities. So I have F1 is whether these devices or whether these implementations actually support custom operators and custom data types. F2 is whether they support unstructured and sparse data, and F3 is whether they support determinism and reproducibility. So you can see not all of them support all, but of course our implementation, this Flare, supports all different optimizations in one, or all different functionalities in one particular implementation. So the implementation itself is very much the same as I discussed earlier. So we have now just integrated into a switch. So we have many switch ports. We have, of course, a parser in the switch. We have our PSPIN processing unit in the data path of the switch now. After the processing, we go through routing tables and a switch crossbar, and then we leave the switch again. There is no host in the switch, of course. There's no main memory. But we leave the switch again through the ports, in this case, the output ports. We have the same architecture, packet scheduler, command unit, cluster scheduler, DMA units, and these various types of memories as we had before. So just to make us all understand Allreduce a little bit better, Allreduce actually can, as I mentioned, reduce quite large data with different packet sizes, with different packets. So I may have a single message to be reduced that consists of thousands or even millions of packets. So here I'm assuming that there are 3 different hosts. Each of those hosts sends a stream of 4 packets, and that's the second index in this tuple. And each of those packets, each of those packets can come from different hosts. So 0, 0 means packet 0 from host 0, 1, 0 means packet 0 from host 1, and 2, 0 means packet 0 from host 2. And of course, the reduction itself has to be done blockwise. So all of the equally colored packets have to be summed up to each other and not differently. So at the end, I will get 5 reduced packets out of the switch. And now, of course, these don't arrive at the same time. So now we could look at the different arrival rates. So we can have 4 cores, for example, in the processing device. And now we have 3 packets arriving, the 3 0 packets arriving at about the same time, but they're not strictly synchronized. So this means that a packet from host 2 may arrive here at time 0, then packet from host 1 arrives at time delta, and then packet from host 0 arrives slightly later because there is some desynchronization or some slack in the network itself. And this means that the buffer for this packet is occupied for a pretty long period. Actually, we may need additional buffer because core 3 may receive a packet from host 2 even earlier than the processing of packets from these other hosts. So from packet 0 is actually finished. So there is a pretty complex schedule that may result from this, that may actually require a lot of buffer space to buffer these different packets or these different blocks of packets. So here's just one particular example, but you could now imagine arbitrary examples depending on the packet arrival from different hosts. So now the question is, how do we manage this? Well, one problem is actually if we stash all this data into a single buffer, like let's just look at a single packet arriving here. This is just packet 0 as a particular example. So here we have a buffer 0. So let's say packet 0 first arrives from host 0, and then it's simply assigned to the buffer. And then the next arrival is from host 2, but there needs to be some processing time here in blue. So it actually arrived here in red, but it cannot be written to the buffer yet. It cannot be added to the buffer yet because the copy from host 0 is still going on. Once this copy ends, I can start the addition of a packet 2 into the packet 0 case, but then already packet 3 is arriving, and actually packet 1 is also arriving. So you see everything that is in red here is actually blocking a processing unit and is blocking buffer space. So that is not such a great idea. Because now we are wasting processing time in this red time and buffer space, because I can only add to a buffer if I can access it exclusively, either through atomics or through locking, but both will essentially have the same effect. So one of our key ideas in this work is, well, why don't we actually send the data in a staggered way? So here we see that the data, each host sends first block 0, then block 1, and then block 2. But if we send them in a staggered way, so host 0 sends block 0, host 1 sends block 2, let's say, and host 3 sends block 1. So just in some permutation, then we reduce the number of conflicts on those buffers, we reduce locking, and it sounds like we may need more buffer memory, but actually what we find is that this is not always the case. So we always get better performance, but not necessarily consume much more buffer memory. So now, just looking a little bit at the results, we can see that these are actually relatively comparable to existing implementations. So SwitchML itself operates at a couple of terabits per second. So now we are not talking about a single device, but now we're talking about a switch. So a switch has lots of terabits per second bandwidth, so up to 52 terabit switches we can buy today. And so the reduction bandwidth is actually significantly lower, so not necessarily all ports can always perform full bandwidth reductions. But you can see here in the data that SwitchML is actually competitive. SPIN, our SPIN implementation that we call Flare, is actually competitive with many of the other implementations. So The required bandwidth is also usually, or the delivered bandwidth is also usually higher than switch-ML, which has a bit of a problem because it is, of course, straitjacketed by the P4 programming model, which we could also talk about later if you're interested in this. So now we have a real example, the ResNet-50 training. So we just act as if we were going to train ResNet-50. And the idea here is that ResNet-50 in the backward pass, in a data parallel fashion, has all these Allreduce operations where we need to somehow compute the sum of all the gradients. In this case, we are actually comparing two implementations. So one is an implementation that is taking advantage of a very high level of sparsity, 99.8% sparsity. It has been shown that you can actually train with 99.8% sparsity in the gradients. And the second one is just applying the dense rules or the dense reduction. So here we compare the host-based dense reduction. This is the time, so the lower, the better. Then we compare the flare dense reduction. So we can see the factor of 2 here, right, which makes perfect sense because we are actually saving. So this is the execution time, and this is the traffic we are observing on the network. So we are saving 50% of the traffic sent because we only send it once up the tree and receive it once down the tree instead of twice up and down the tree or in a ring, in the host-based variant. If we now employ sparsity, the 99.8% sparsity, the host-based version just gets barely better than the flare version because it still sends much more data. And the flare version, of course, does not gain a factor of 500 like you may imagine here, going to 0.2% of the data, but it gains a significant factor. Why does it not gain the factor of 500? Actually, you can see here in the data volume communicated, it gains a huge factor, but the runtime itself is not as impressive because now, of course, you need to interpret the sparsity structure. You have a lot of overhead actually working through the sparse representations, and since we still have a general purpose CPU, we are not able to lower this overhead further. But now you could think about specific optimizations for sparsity on these architectures. So in fact, we already, in our collaboration with Luca Benini, we already have a thing that's called ISSR, indirection stream semantic registers, that we could easily employ in the SPIN-NIC optimization framework in case this turns out to be a bottleneck. Okay, so with that, I would like to finish my presentation. And I talked about the motivation and overview of SPIN, so reminded you again what this is all about, told you about the several new use cases that we introduced, told you about a complete hardware implementation in collaboration with Luca Benini's group, and a new idea, a new direction we are going for in-network Allreduce. As I promised you, this is all available on our GitHub, so you can just download pretty much the whole hardware design, the whole software setup, pretty much everything to run it. And then once you have it downloaded, you can synthesize your CPU, you can your SPIN or PSPIN unit. You can double check the area and energy efficiency, reproduce it yourself with this niche cluster now, so it's even slightly better than in the original publication. So this is always moving forward. You can implement very large-scale simulations with using SST and varilator together or tied together with cycle-accurate simulation in the varilator framework, and then SST for the network to set up larger clusters. And of course, you can reproduce everything in the programming interface, so you can program these devices and work with them as you wish. So with that, I would like to would like to end my talk and also let you know that in my lab there are always open positions for PhD students and highly qualified postdocs. So let me know if you're interested in this, and look at our webpage if you're interested in this, that you can see down there, and maybe apply or contact us otherwise. And I'm open for questions now. Thank you.